This is further stats 2 from 2021. The first question is about Spearman's rank. We've got some missing ranks here. Now there's 3 of them here, and we're missing 3, 4, and 5. So this is each one of these S's is going to be 3 plus 4 plus 5 over 3. Of course, that's obviously just going to be 4, right? We just need 4, 4, 4 here to make this balance out. But in any case, T's here, we're missing, well, we've got 1, 2, 3 there, so we're missing 4 and 5. So 4 plus 5 over 2 clearly gives us 4.5 as our missing ranks there, so not too hard. Now the PMCC is used instead of the Spearman's rank formula for this. And they're just saying, why have they done that? Well, because when you've got a few too many ties, this becomes less and less accurate. So if you've got no ties, or even just 1 or 2, maybe, you can do, but the more ties you have, the more inaccurate this is here. So that's why they've stopped using this. And then state your hypothesis clearly. So okay, well H1 is that rho is going to be 0. And then H0 is rho is 0. And then H1 is that rho is greater than 0 because we're testing a positive correlation here that higher in history, higher in geography. So it's a one-tailed test. And then we just need to look up, because we already know the R value that they've actually given us already, so we don't need to calculate that. We just go to the Spearman's coefficient because they used the ranks here. They used this, but they used it on the ranks, so it's still a Spearman's test. And it's two-tailed, like I said, it's one-tailed, like I said, 5%. So that's going to be this one here, with N is 7, I think, up to G is 7, so that's going to be this one here. And I think this is bigger than this, or in other words, the test here is less than. It's not really a test, it's a thing that we've calculated. Is less than, it's not in the critical region, and so therefore we're not going to reject H0. And there's not enough evidence to suggest that there's a positive correlation here. Throw in some context, always a good idea to throw in some context. But otherwise, that's that question done. Question 2 then, so we've been given some standard deviations here, which is interesting. Got some samples of the 2 different things, we've got some mean times. State your hypotheses clearly. So the hypothesis is going to start with that the blue candles last 5 minutes longer than the white, and then the H1 is going to be that it's more than 5 minutes longer. So this is going to be our H0 and our H1, looks like. So that's good. And now we've got loads of information from the formula book. I mean, the formula book is your best friend in FS2. Not everything is in there, like in FS1, but lots of stuff is. We can see here, when we've got random samples from 2 different normal distributions where we have the information, we can test it using this massive formula here. So okay, that looks good. So X bar is just going to be 39.5, Y bar is going to be 33.5. Mu X minus mu Y, we're going to use our H0 to do that. And you can just see from here, this mu minus this mu is just equal to 5. So that's going to be replaced with a 5. We know our 2 sigmas from the original populations, and we know our n's, of course, from the samples are just 80 and 90. And that'll be everything that needs to go in there. Like I said, this stuff just turns out to be 5 based on H0. We type all that in, we get this. And of course, this is going to be a normal test. So we're going to break out the normal distribution tables here. You could, of course, just use a calculator for this. But I have the normal tables to hand because I'm using the formula book a lot here. And it's a 1% level significance test. So we're going to do is one-tailed, of course. So it's going to grab the 1 thing there, 0.01. That's the statistic right there we're going to use. This is less than that. So again, we're still not in the critical region, just like we were in the last question. That we're not going to reject H0. Throw in some context, so there's not enough evidence to suggest that the mean is greater than 5 minutes longer than the one before it. I haven't written the context down, just for safety, just always write down the context at the end. I think I just ran out of space to write things. Anyway, explain how the hypothesis could be carried out differently if the variances were unknown. So if the variances are unknown, you need to get some unbiased estimators for that. And then you can also use the t-distribution from there. And saying those 2 things will be more than enough to answer that. The burning times of candles may not follow a normal distribution. Describe the effects that this would have. So the thing is, because you're taking quite large samples, the sample means will follow a normal distribution anyway, based on the CLT, the central limit theorem, from FS1. So interesting that they've given you a mark here for remembering some FS1 stuff. But yeah, the sample means will follow normal distribution anyway, so it doesn't actually matter. In FS1, you learn you can do CLT on things that aren't normally distributed because the means of the sample always will be anyway. So the test will still be valid here. It doesn't actually matter if that assumption is wrong. Good, so question 3 is the best question on here because it's the one where you actually use some maths. They've given us the cumulative function. And so if we're doing this, like normally, if they gave us the density function, just little f of x, what you would do to do this, or to get this, is you would integrate that and then sub in, from because it starts at 2, from 2 to 5, and then also integrate from 8 to 10, I guess. because it stops at 10. But you've already got the integral. So all you have to do is take this function here and plug in 5 and 2, as if you've done some integrating already, because they've given you the thing that the function will integrate to, because that's what this is. And then just add to what happens between 10 and 8. And of course, you sub in some values here, and lots of things cancel out. You type in the calculator, you get this here. The median of x, now that's the value for which half the data is beneath it. So from the community distribution function, it starts at 2, and it just goes up to m. We'll call m the median, and that's equal to a half, because up to m, there's a half of the data there. And again, we just substitute these two things in, stuff will cancel straight away, and you'll end up with m is 10/3 pretty quickly. Find e of x squared. Now, again, go to the formula book here, because you've got some really useful stuff about continuous distributions. If you're doing e of some function, so the function is x squared, I guess, so g of x is x squared, you need to integrate g of x with f of x. Now, that's little f of x. So finally here, I do need to differentiate this here to get little f of x. This is, of course, just 2.5x to the minus 1. The minus 1 comes down, makes that positive, goes to a minus 2. So that's good. And then I can just integrate this with an x squared. And between 10 and 2, of course, because that's where the function starts and ends. And this cancels with this immediately, which is really nice. So it just integrates to 2.5x. You put in the numbers, and you get 20. Sketch the probability density function. So what do we know about this? Well, we know it looks like this. And from like, what, year 1 regular A-level maths, you know that a function of something over x squared, kind of, if you imagine the axis here, does this and this. It looks like 1 over x, but it's both in the top half of the graph. But of course, we're only interested between 2 and 10. So it just does this bit between those two, a bit like that. When you plug in x as 2, you get this value, which I thought I'd add. I think it's probably unnecessary, but I thought I'd add it as in anyway. You could plug in 10 as well and get what the value is here, but I couldn't be bothered. And yeah, this is this skewness. If it's more so over to the left, that's positive skew. If it's more so over to the right, that would be negative. But I think that's that question done. Good. Number 4 then, got some statistics here about mean temperature and elevation. So that's cool. So we have all of this. Good. Product moment coefficient is this. Interpret this value. Well, this is negative correlation, so that means an increase in elevation means a decrease in temperature, or something to that effect. Right context. Better be safe than sorry. If you just wrote negative correlation, that's no marks. Put in some context here. Show that the equation of the regression line is this. There's a lot of things to piece together here. Again, go to the formula book. Look, you've got some information here. So this will help. This is what we're kind of going for, where y is t and x is x. So that's fine. And the a and the b are the thing we're trying to sort out here. A is the y, the mean of y minus the b times the mean of x. So of course, all of that I think I can find as long as I have b. So b, again, from the formula book, is this. Now we look up here, and we actually only know s of xx, or tt. We don't know the cross bit. But that's okay, because that's where this comes in. And one final piece of information from the formula book is this. So we have the r, right? They've told us the r. And we have these two things, they've told us those. So I think we can solve to get the cross thing here, sxy. So we multiply across and we get this. And now we can put that into here, along with, and now remember the x's are just behaving like x's. According to this formula here, it's the y's that become t's or whatever. So we're going to use this divided by the sxx, which is that, to get b, which is this. That's good, because that matches up. And then finally the a, well, y bar is just going to be, y is t, remember. So y bar is this divided by 20. Just the sum of the thing divided by 20, and an x bar is going to be this divided by 20, and therefore a is equal to this one minus this, which will actually 2 minuses will make a positive, times this, and we'll eventually end up with what they wanted us to get, which is that, and we'll have our answer there. The random variable w represents the elevations in kilometers instead of meters, which it originally was in. And it says to write down the equation in terms of that. A couple of ways you could do this, like obviously when x is 0, when you've got no elevation, this number represents the sort of temperature when you're at sea level, I guess. And that's not going to change whether or not you measure in kilometers or meters, because you haven't measured upwards if that's 0. So that number is clearly not going to change. And what about this number here? Well, if you're measuring kilometers, you can just think, well, your number's going to be much smaller here, so therefore this one's going to have to be much bigger to compensate. And that's literally the logic that I went through. If you want to be a bit more intelligent, you can make a proper substitution and say, x in meters is given by 1,000 times the equivalent in kilometers. But I mean, sure, you get this eventually anyway. And anyway, show this RSS for this model is this. So formula book, again, tells us how to do this. We've got this one here, which is the STT, which is that one there. SXY we worked out before. SXX we've got here. We can put that in. You could have also used this one instead with R, because they give you R as well, but I just used this one. And you get that for a free mark. What are the weather stations has a recorded elevation that and an annual mean temperature of that. So, okay, what we can do is we can go to our regression model, and this is in meters, right? So we'll use this one here. And we can substitute in 1,100. And we can just see what the temperature would be based on the prediction of this model. And it would be that. And now that's quite far from this. So what we'll do is we'll work out the difference and square it, because that's literally what the difference, the sum of squares difference does. It works out the difference between the actual value and the predicted value and squares it. And when you do that, you get this number. And that's quite a large proportion of this. In fact, we can do it, right? It's like working out your percentage in a test. It's this over this times 100. And you get this. And so a large part of the sum of squares, the total sum of squares, is coming from this one piece of data, which suggests that that piece of data is probably an outlier. If 80% from 20 different things, 80% is coming from one piece of data, that's probably an outlier. So yeah, that's what we'll say. Question number 5 then, I do like these questions as well actually. Got uniform distribution between 0 and 4 beta. Uniform distribution is of course just a rectangle like this. So we could note that this maybe is 1 over 4 beta. We don't actually end up using it, but it's just this times this has to be 1 to make the total probability 1, I guess. And okay, so we've got this. Now the mean of this thing here, mean of x, or e of x, is clearly just 2 beta, right? Because it's got to be in the middle, which is, because it's uniform, it's just half of this. So that's clearly just 2 beta. And now we're working out the biases of this. And by definition, the bias of some statistic t, so these are the statistics, the bias is expected value of t minus theta, where in this case, theta is going to be beta, because that's the thing that we're estimating. Okay, so all we have to do is work out e of a and then take away beta, and that will be our bias for this one. And then e of b, take away beta, that will be our bias for this one, and so on. So okay, what's e of a? Well, the half doesn't matter, so I can just bring that out to the front. E of two observations added up together is just e of the first plus e of the second. And of course, e of each one of those is 2 beta. So this makes a half 2 beta plus a half 2 beta, which is just 2 beta. And then, like I said, we do e of that statistic minus the thing that we're estimating. So we're going to do this minus beta to get our bias of beta. 2 beta minus beta is just beta. So that's our bias for A. Moving on to B then, exactly the same thing, just work out the the expected value of B. The eighth can come out to the front to get this. We can split these all up as well. And then this 2 here can also come out to the front, and this 3 can come out to the front there. And then, of course, each of these is 2 beta. You can do this with much less working if you want to, but each of these expected values is 2 beta. You can work all that out, and you get 1.5 beta. Take away the beta to work out the bias, and we get 0.5 beta. So this is a slightly better estimator than A is, because it's got a lesser bias. C then, exactly the same thing. I'll go through it a bit more quickly this time, just because I can't stress enough that it is exactly the same thing as we just did, just with slightly different numbers. And I believe that should be a minus, should it not? Because, oh no, of course, sorry, the answer was a minus, I remember now. 0.5 beta, and then you take away the beta to get the bias, and you get minus 0.5 beta. That's what I'm remembering. Yes, that's good. So we've got our 3 biases, good. By calculating the variances, explain which of B or C is better estimator. Now, what this tells us is that B and C are better estimators than A, because they're closer to having 0 bias, but they're equally far away from having 0 bias, of course. So, which is the better estimator? Well, if they have an equal amount of bias, which these essentially do, then whichever has the lower variance would be the better estimator. So let's test that then. So let's do variance of B and variance of C. Now, I think before we have to do that, well, I'll make a start, I guess. Remember, when you're dividing these observations by something, you can bring it out to the front, but you do have to square it. This is all in chapter 4. When you have a scale factor on an observation, you take it out, then you have to square it. And we're going to do the same thing to these 2 things as well after we split them up. When we bring this 2 out, we're going to square it. So this can become 2/8 squared, and this can become 3/8 squared. So we'll get all this. Now we need to know the variance for each observation. So what's the variance of the original thing? Well, the table actually helps you out. The formula book, I should say, has a little very helpful table on it about uniform distributions. The variance is given by this, so that's super helpful to know. Also, just note we could have got the mean through this as well by doing 0 plus 4 beta divided by 2, which is of course 2 beta. But the variance is just right here. So the variance of this function is given by this, where this is 4 beta and this is 0. And so that's just 4 beta squared divided by 12, I guess is what I've just put in there, super lazily. And then I think I literally just ignored the betas and typed all of that into a calculator and got this, and then just put the beta squared back in. So that's my variance for B. And exactly the same thing for the C, for the variance of C. Just note there is one trick here that we need to remember for variance, which is that we always add in, when we're splitting up observations like this, even if we're taking away, we always add the variances. And then again, this 2 comes out, but also needs squaring. And of course, the variance is given by that same thing we had before. Type it all in the calculator, and we'll get this here. And now 1/8 is less than 7/24, so the variance for C is lower, and therefore C is a slightly better estimator because of that variance lower, but the bias was the same. And then it says find an unbiased estimator for B. Now, we talked about this, how this bias is E of t minus theta. Now, if the bias is 0, that means it's unbiased. So therefore, we need E of t, E of the statistic, to be equal to theta. So an unbiased estimate for beta, we need some statistic where if we work out E of that thing, the expected value of that thing, we just get beta. And the easiest way of doing that is to just do something super, super simple like this, right? Because we know the expected value of, say, anything like x1 is 2 beta. If we just divide that by 2, we get beta, which is exactly what we wanted to. So if we work out the expected value of t here, it will just be expected value of this divided by 2, which is 2 beta divided by 2, which is beta. And so that would be the simplest way of doing that. There are, of course, lots of other things you could have done, but that would be the way that we did that. Cool. So now we have 2 different types of butterflies, it looks like, with some data about the sample that she did. And we've got to do a test here, state hypotheses clearly, so we may as well start there. She's testing whether the variance is different. So obviously H0 will be the variances are the same. I've called R just ringlets just big R and these things just MB. And then the alternative hypothesis is that going to be different. This will be a 2-tailed test eventually when we get to that bit. There's some stuff here about unbiased estimators because this is actually relates back to, was it question number 1, where we don't know the variances of the the original populations of butterflies. So we need to create an unbiased estimator. This is the only thing the formula booklet gives you, and in this case, it's not especially helpful. So it's super helpful if you go into the exam knowing this formula, which seems to come up in these papers much more regularly, using this as being much more helpful. A derivation for that is on page 144, I've just made a note of. But anyway, we know all this stuff here for each of these 2 different types. Of course, x bar is just going to be the sum of the data divided by the number that there are. And this is just going to be this one here. And of course, 1 over n minus 1 is going to be this 1 over this minus 1. So we can do that for both different samples. So that's the first one in there. It gives you that. And the second one, similar sort of thing, will give you this. So these are our 2 unbiased estimators. And now if you divide those 2 things through, that will be distributed via an F distribution. So these are our tables. For the F distribution, we're going to do a 1% test because, of course, it's 2-tailed, so halve that for 1%. The first population, so we've got a population of, well, we have to take away 1 from each of the 2 ends to work out our degrees of freedom, don't we, for the F test. So take away 1 from that to get 7, take away 1 from that to get 5. Now, we don't have the 7 in this column. I've cropped it out, but the next one was 8. So we'll do the 5 first, and then we'll find 7 second, and that'll be this piece of data there. So that's the test, that's the critical value for F57 0.01 is that. And now I've put this bit first, and that 5 relates to the middle browns. 6 minus 1 is 5. So that means when we do these 2 things, I do this one divided by that one. Whichever comes first here is the one that's on the top of the fraction when you divide the 2 estimators. So it's this divided by that to get that. And this is kind of weird, right? Because this one is so far below that one, you think you've made a mistake. But it's fine. It just happens to be a long way below it. It's nowhere near the critical region, of course, so therefore we don't reject H0. And there's no evidence to say that the wingspans of, or the variance of the wingspans is any different. Again, throwing in as much context in there as possible is never a bad thing. Anyway, the K% confidence interval of the variance is found to be this. So we're only concentrating on these guys now. So I've left the estimator here. We have this. Okay, so where do we make a start here? So I've got out the chi-squared distribution. The reason I've done that is because the way to do this on page 143. But it gives you a super useful formula, and I'm only saying this because this isn't in the formula book. So this is probably something else that you just need to go in knowing. But the way that they do this is they do n minus 1 here times s squared here, which is just this 4. If you divide that by the critical value from the chi-squared distribution tables, you just get the lower bound, or the lower, I blanked on the word here, the bottom end of the confidence interval. Of course, if you're using this half, it turns out, of the chi-square distribution. You could also just look for the top half and you'd get a different value in here, but of course it would be symmetrical and you'd end up with the same answer in the end. But yeah, this is given on page 143. It's not in the formula book. So of course we can work out this out. We can do 20 divided by this and we'll get this. We look in the in the chi-square distribution and we notice that that's that number there, which refers to a 0.005 test. So therefore, well, where did this alpha over 2 come from? Well, of course, because it's two-tailed, right? So whatever this was, you'd have, taken away 100 and divided by 100, whatever, to get down to your confidence interval, and then you'd halve it to get, because it's a two-tailed thing, of course, with a confidence interval. So that's where this half comes from. So we times by 2 and we get to this, and we think, well, what percent test does 0.01 refer to? Well, of course, it refers to a 99% test. So just working through that backwards, 99% test, it's two-tailed, so you'd halve that for, so you'd say you're looking for 1% either side, but you'd halve it because it's two-tailed for 0.05, and that's where that number comes from, and that's how we usually do it forward. But we just essentially did all that backwards to find this 99 here. Anyway, calculate a 95% confidence interval for the difference between the mean wingspan. So I've still got my estimators up here, which we're going to need. We are also going to need the means, which of course is just this over this and this over this of each sample. So that's fine. And what we're going to do here, again, just from the formula book, I try and paste everything from the formula book into this work here, just to make it very clear that you can find this stuff. But what you need to do here is a couple of things. You need to find a pooled estimator based on both of the previous ones that you had. Now, that's not too hard to do because we know there are 8 of these and 6 of these, and then we do -1 for each, and then 8 plus 6 minus 2. And we can just plug those two numbers in and we'll get our pooled estimator. So that's not too difficult. So that's where that comes from. But also, after we do that, we're going to take that value and put it in here. And we are looking for the confidence interval here for the difference between them. Sorry, I don't think I'm actually going to use this. I think we used this earlier, which I think is why I put that up there. But anyway, we find the pooled thing here. That's on page 180 as well, even though I just showed it up there. We have this thing here, which is it's very similar to what was in that book, but it's not quite exactly the same, but it is very similar. This is, again, from page 182, so it's the same kind of area. We have the two means taken away, plus minus the statistic from the t tables, times that pooled value. Remember, you have to square root that because we found the squared one here, so we're going to have to square root that there, and then plus or minus this thing here. Again, this is not really in the formula book. It's close, which is why I put this up here, but it doesn't really tell you too much about the confidence interval there. So you probably best off going in knowing this. When we're looking for the t-distribution figure, where am I? There it is up here. We need to do 8 plus 6 minus 2, which is 12. So we're going to go down to 12 here. And then it's going to be a 95% test. So it's going to be 0.05, I guess. Except it's two-tailed, of course, because it's a confidence interval, obviously. So it's two-tailed, so we halve that down to this. We find this here. So that goes in there. The root of this goes in there. Everything else we just have, so it's not too difficult. Like we have these numbers here. We have this. We root it. We have these two things, we have those up there, and we just type all that into the calculator, and you get both ends being this. And I think that's the whole question, and we're on to the last thing here, which is good because I'm starting to lose my voice, I think. The weights of a particular type of apple are given like this, and the oranges are given like that. Find the distribution of A plus R. So that's very simple. There's no multipliers going on here, so we're just going to add the two expected values, add the two means, and we're going to add the two standard variances. And we'll just immediately get this. This is 144, this is 100, so we just add them up. And I wrote it the super lazy way, so that's fine. I've called that Y, just because we're going to need it later. And the total weight of 2 selected apples, well, that's just the same thing, but here twice. So you do this plus itself, and you do this plus itself, and you just end up with this. And I've called that X, again, because we're going to need that later. In fact, we're going to need it right now. A box of 4 contains 4 apples and 1 orange, and we select 2 pieces of fruit random. Now, if you do that, there's one of 2 things can happen. Either you can get 2 apples or you can get 1 apple and 1 orange. You can't get 2 oranges because there's only 1 in there. So let's just think about the first case first. Let's think about what happens if you get 2 apples. Now, what's the probability of that? Well, it's just 4/5 times 3/5, right? You take an apple first, that leaves behind 3 apples and 4 in total. So just 4/5 times, 4/5 times 3/4 is what I should say. 4/5 first because there are 4 apples out of 5, and then after 1's gone, there's 3 apples out of 4. Those two things cancel, you get 3/5. Now, if you do that, what's the probability that it exceeds 310 grams? So we're looking at this distribution here for the 2 selected apples, and we're looking at the probability of something being drawn from here that has a weight of above 3 or a mass of above 310. Of course, the probability of that is 1 minus being less than 310, and we can just go to our calculators here, and we can do a cumulative normal thing with root of that as the variance, of course, and we'll end up with that figure there, and we'll end up then with that there. And now what if we're in the second case? What if we've taken one orange and one apple? Well, then we're doing this distribution, aren't we? And what's the probability, by the way? Well, it's 2/5, because those are the only two things that can happen, aren't they? Apple, apple, or apple, orange. So 2/5 is the chance of doing this other thing. And the probability, based from this distribution, of being greater than 310, well, again, we just do 1 minus the probability of being less, and then we use this. That should be a y. That's just bad copy-pasting. We do this distribution here, with, again, root of this acting as our variance, and we get this, which is this. And so the probability in total is the probability of this happening, this case happening, 3/5, times the probability of it being greater than 310, plus the probability of this case happening, times the probability of it being greater than 310. So just this times this, plus this times this, and we get this, which is equal to that. And that would be the answer. The very last thing that we have to do in here then is that we have, this person is selecting M apples and 1 orange, and they're doing this to it. And we need to find, well, they've given us the confidence interval to a 95% thing, and we need to find M and N. So we're going to do some actual proper maths right at the very end of this, but we need to set it up first. So firstly, just to give you an idea what this is doing, W is a bunch of A's added together, in fact, M of them added together, and then minus N times some random one from the oranges. And this is important because that's going to square the variance, remember, because you're timesing one particular thing. So the expected value of W is just M times the expected value of A, because there's just M of them here. And then this N here can just go out to the front because expected values don't get multiplied by anything squared or anything, they just move it out to the front. So you just get M times the expected value of A, which is 160, minus N times the expected value of R, which is 140, and that's our expected value for W. Now, I think I then started talking about the variance, and again, because you're timesing this one by something, that variance is going to square. And also, of course, we talked about before, it's always going to add in. Variance is always add in. So we have this, and okay, cool. Now the variance, we're going to need to find out more from here. Sorry, the variances we have from back here, right? 12 squared is 144, and 10 squared is 100, so we get this here. Now, what we're aiming to do is set up a simultaneous equation in M and N. And now this bit isn't too hard to get because the confidence interval, if you just add up each end and divide by 2, that gives you the mean of the distribution, because it must be symmetrical around the mean. So that must be the mean, which is the same as the expected value. And so therefore, we can just say 1,300 is equal to these two things here. And I'll put that in red because that's super important for later. I've just written that W is this distribution, I guess, because that's the expected value and that's the variance. I don't think I really needed it that much. Anyway, so we've done that bit. Now, how do we deal with the variance of W, and how do we get some figure out of this that we combine with this to make M and N? Well, what we can do is we can again think about this here, and we can use this idea that the width of an interval is 2 times the Z statistic times sigma. Now, there's a couple of things going on here. Firstly, I can't really use either end because I would need the, or actually, no, I could because I do already have the mean. So I could have used either end. But there's a useful formula given here about that the width is 2 times Z times sigma. Now, usually that formula is sigma over root n. But that's when you're doing a sample of like n things. And we're not really doing a sample. We've got a whole distribution here. And we're just thinking about its confidence interval. So there's no sample going on here. So there's no n down here. You could kind of think of just n being 1 because you almost just imagine taking one thing from this distribution and that the confidence interval is there. So you can think about n just being 1 there. And divide by root n is just divide by root 1, which is not doing anything. So the width of confidence interval is this. The Z statistic is from the normal distribution for 95%. But of course, it's two-tailed, so we halve that down. And we get this figure here, which you're allowed to just write down without any quoting at all. So it's going to be this times this. The width is obviously this minus this. Equals to this. Sigma is, of course, root of the variance, so it's root of all of that. We can divide by these two things and work out that, and we get this. And good. So we have this. Now we have this, and we have this, and now we just get to do some proper maths, right? We just need to figure out M and N from here. We can square both sides here. We can rearrange this for M, I guess, and then just substitute this M into here. So M is this divided by 144. So I'm just going to put that in there. We can multiply this out. I think I actually multiplied everything, I think, by 9 here. Does that make sense? Is that a thing? Yeah, just because it cleared out any fractions like this over this gave you like something ninths, like 10 ninths or something. So timesing by everything by 9 just clears that all out. Rearrange, you can just put this straight in a calculator because you're not messing around, you're just doing a statistics paper. So it goes in a calculator, you get this. This obviously doesn't count because n needs to be a whole number. It's n was originally about, oh, it told you, I think, up here, n is a positive integer. So it can't be this. So we cross it out. If n is 9, you put it back in here, you find out m, and you get this. And those will be our two answers. Thank you for watching, and I'll see you next time.